of those, in order to stop it from going any further, we're going to cool that way down, right? Temperature control is critical, because if you do this at room temperature, you're just going to end up with an alcohol, right? A primary alcohol. So, well, 2 alcohols. Yeah, you're gonna end up with 2 alcohols if you do this at room temperature. So, it actually can react at whatever temperature, and it'll just go as far as it wants to. So, low temperature is very critical. Just don't touch it. Reduction of amides. We can use LAH. LAH is nice and incredibly aggressive. So notice that we always have a 2 by this water. That's because we work this up with water. But that's a whole second step, because we're not just throwing in LAH and water, because, well, that would be a really violent reaction that would give us nothing useful, because you would have hydride, and the easiest thing for hydride to attack would be water, because water can be deprotonated, and so you would have a nice you would make hydrogen gas and a weakness if you just throw those in together, right? Very violently too, which I don't know if it's violent enough to actually catch that on fire, but you're making hydrogen gas, so like, I don't know, it doesn't take much to catch that on fire anyway. Depending on the degree of substitution of your amide, you're gonna end up with a primary, secondary, or tertiary amine. But regardless, you end up with an amine. And whatever was bonded to that nitrogen is all the same things still bonded to that nitrogen, right? So it's basically nucleophilic attack of a hydride. Sweet, okay. So yeah, this is nucleophilic attack of a, do you guys remember these? Were these a staple of your childhood? Okay, all right, I'm just making sure that I can't remember anymore. I can't tell anymore. You guys are like younger than my younger brother, so I don't have like a, don't know.
I feel like that was like off-brand, like Kids Pop or whatever.
Oh, no. Now was like
for our generation.
Oh, okay. Because now, well, yeah, fair enough, because you guys had, I mean, I had an iPod in 6th grade, so you guys, by the time you had your own music, you pretty much had, like, you could buy individual songs. Yeah, we couldn't buy individual songs, so if you wanted just, like, you know, some of the popular songs from the radio and, like, from the radio and not just, you know, then people had the Now CD. I don't know, the cool people had it. I specifically looked at that. I had this joke up from last time, and I was like, oh yeah, I forgot about that. I'm gonna go see if I can find one from 2000. So that one's from 2000. You're welcome. So we're not gonna do that mechanism. I can unhide these slides so you can look at it real quick. But basically, we could just as easily draw this as H minus, and you can put it in quotes if you want to remind yourself that it's not actually H minus, it's, you know, stuff, but like, that's basically what it is. So you have basically an H minus attacking your electrophilic carbon, and who cares about this stuff? That weird, it's not a curved arrow, so it's not a mechanism arrow, it's just, I don't know, complexy stuff, and we're not an organic chemist, so we don't care where the metal goes or what happens to this. It's still just a negatively charged oxygen, so whatever, right? We wouldn't have to draw that. We get our little tetrahedral carbonyl addition intermediate, and then we break our bond, and we end up forming a CN double bond and kicking off the oxygen, which is also part of why I'm not gonna make you know this mechanism because I hate these like fake, I don't wanna have to care about where the metal goes, but you straight up have an oxygen just, like a negatively charged oxygen is a leaving group. So it leaves as a O2 minus, because you can't protonate it, because if you were able to protonate it, if there were any protons available, you would have just made hydrogen gas, right? So, just because it's hanging out with the metal, it's fine, I guess. Yeah, you don't have to know this mechanism. It's, I don't know. But then you undo your double bond there with another mole of your hydride. So, reduction of nitriles. We can take a nitrile and we can turn it into an amine. It's always going to be a primary amine because, well, back here we had whatever's attached to this nitrogen stays attached to this nitrogen. That's what we get. Whatever is currently attached to the nitrogen will still be there after reduction. It's the same thing here, except, well, nothing's really attached to that. I mean, that carbon is just really aggressively attached to the nitrogen, right? And we're reducing to get rid of the aggressiveness of that connection, so they stay connected, and then, well, reducing agent, so basically hydride, and we just always end up with a primary amine. So yeah, you can get that. We did it! We made it through chapter 18. It is 8:42. I vote we have early break, and then we start on chapter 19. Yeah. Yeah, let me know if you have questions or want to go over stuff or whatever.